Hey everyone, and welcome to a discussion on the cosmological constant, which is a particular form of dark energy. And again, just a brief review of that, it turns out that we're not sure exactly if the vacuum energy density of space itself is truly constant or if it can change over time. And measurements to refine that, again, are based upon what's called the dark energy equation of state. Basically, if it's equal to -1, which is consistent with our best measurements, then that means that it is truly a cosmological constant. But we're not sure if it's constant yet, and if it's not, that certainly is very exciting. There's certainly a lot of possibilities within our best measurements, so stay tuned for those. Keep your eye on the dark energy equation of state and various research collaborations that can shed some more light on what this stuff really is. But first of all, I want to talk about the cosmological constant problem, if you will. It's very interesting. And here on the right, this is a great review paper. I'd highly recommend if you wanted to know anything you ever wanted to know about the cosmological constant problem, but were afraid to ask. And so there's a myth that surrounds it. It's basically if you calculate the cosmological constant using the standard model of particle physics from vacuum fluctuations, the result is 120 orders of magnitude larger than what is observed. And that's really a rather pervasive myth, but it sounds really nice and has been featured in a number of fine-tuning types of arguments that people have made. The abstract, this review paper reads, "It is far from being 122 orders of magnitude larger than the critical density is often quoted in the literature." So where does this number come from? What is a better way to phrase this, and does the discrepancy come from in the first place? So one idea is that this isn't really a problem, or at least it wasn't a problem until the particle physics community came in and tried to explain how we get this vacuum energy. It's not really something that's very strange. It's just a catchy name. First of all, dark energy for the observed acceleration of the universe. It's a rather natural thing to add to the equations of general relativity, and the effects of it, again, were so small we didn't really notice it until the 90s. And its intensity, it's just this fundamental constant lambda on the right in the middle of the equation there, and we just measure it. And that's it. It's a rather simple physical theory, and that's all that there is to the cosmological constant. However, it turns out that there are some rather confusing things about it, and some questions that people might wonder is, how can it be that the density remains constant as the universe expands? Don't you need to get that universe or that energy from somewhere? It turns out that no, you don't, but we have to take a look again at where various conservation laws come from. But this can be a rather mysterious thing because we have this idea or sense that, oh, there is this absolute law of the conservation of energy, and that's really not how physicists think about the conservation of energy, and thankfully we have a mathematical tool to do that. But basically, you get conservation laws from underlying symmetries. But it turns out that energy isn't actually conserved in general relativity. Maybe there's some ways that you could rearrange the equations, but it's not really a problem at all for cosmologists. Why? Well, it turns out that energy conservation occurs because of time translational invariance. And what does that mean? Well, it basically means that the background on which particles and forces evolve, as well as the rules governing their motions, are fixed, not changing with time. And that is a little bit of a mouthful, but because that's the case, that the background on which particles and forces evolve isn't changing, and the rules governing their motions are fixed, you basically end up with the conservation of energy. And that describes how we look at the world around us, but that's not really the world of general relativity, because space and time are dynamical objects and do evolve with time. So basically, Noether's theorem doesn't even apply to the equations of general relativity. It doesn't, and that's perfectly fine. And if it doesn't apply, then energy need not be conserved. So it's not really strange to have a particular field that does something like that. To be a little bit more mathematical about this, there's an important equation to consider, and this is another mouthful, but basically this is that non-gravitational energy and momentum are conserved. And it's a rather simple concept that if space-time is still, then the total energy is constant. But if space-time is evolving, then it's not. And that's it. And this is not really a thing that is very strange or spooky or bizarre. This is just a property of space-time itself. And so if you have more space, you just simply have more of this stuff, but you don't need to invoke any kind of extra explanation to try and say where all of this energy is coming from in the first place, because Noether's theorem tells us we're not even breaking any laws of physics in this particular case. And so, but it turns out that despite all of this, there's still a lot of confusion about this rather simple concept. And so here's a little picture on the right. It says, overthinking the art of creating problems that weren't even there. So one of the interesting things about this cosmological constant is there's no natural way to derive what its fundamental value is. It's just a fundamental property of space itself. Similar to how you have different types of particles and they just have fundamental properties. You can derive some of their masses from scratch, but others, they're just simply properties of the universe, and that's it. However, we want to be able to explain things as much as humanly possible. And so along come particle physicists and say, hey, vacuum energy, we know what that is. Because you can add up these terms from quantum electrodynamics, quantum chromodynamics, quantum field theory, and you get the vacuum energy is, you get a value for it. But the only problem is that when you do this, you get a value that's a billion, whatever times larger than the cosmological constant. And so it's basically that, hey, obviously our calculations aren't wrong. And so this is a problem for you cosmologists. And it's like, wait, we had no problem to begin with. A quote from two cosmologists down there is in the bottom left. Every reasonable person would conclude that there is something missing in the particle physics argument, especially knowing that the argument is already known to be wrong in flat space. But at the same time, this creates the basis for the cosmological constant problem, where you basically have trying to explain what this vacuum energy density is from quantum mechanics, and then you get a result that's way bigger than what we actually measure. And so it'd be pretty reasonable to assume that well, maybe there's something wrong with the quantum calculation. But at the same time, it's a rather interesting thing. So I'll talk about a little bit more about where this number comes from, how you could get that, and what are some solutions to the cosmological constant problem. It's an interesting question. So first of all, it's simple enough, so to speak, how you might calculate this. Now, there's a lot of terms here, and you might not think that it's so simple, but the ideas aren't too complicated. So there's the first term that basically depends on the masses from particles in the standard matter, standard model, times and they're scaled by this little factor called mu. And I would highly encourage you to go through, which is a renormalization scale, to go ahead and look through the paper if you want to see a derivation of that and how you could get this. Basically, that's what the first term is. You basically add up the mass of stuff in the standard model. And then you include, there's the second term there, which is a row of B. That's called the bare cosmological constant, which is a very interesting term that we'll come back to. And then there's the third term that comes from this electroweak phase transition, and then the strong force phase transition, and there could be other phase transitions that go ahead and could contribute, but we don't have experimental evidence of any phase transitions beyond those two at present. So what do you do when you get this? You add up all of these terms and you find that the density of the vacuum is something around 10 to the 8th giga electron volts to the 4th power. Now that might sound a strange way to write the energy density in terms of energy to the 4th power, but it's a rather natural way to write it. And how does that compare though to the measured value? Well, it turns out that if you compare the two, you can find that the calculated value is about 10 to the 8th giga electron volts to the 4th power, and the measured value is 10 to the negative 47. And so this is not 122 orders of magnitude, but it's still 54 orders of magnitude, where basically if you calculate this number from various quantum models, and compare it to the measured value, there's a huge difference between the two. And so basically, that leaves us kind of with this problem where we don't really know where the measured value of the vacuum energy density actually comes from. However, you could write this in different units as well, and write this instead of in units of energy to the fourth power, you could write this in units of mass. And if you do that, now this only becomes a 14 orders of magnitude problem. And so while that still could be seen as a problem, the difference is really not that big whenever you write it in different units, which is kind of a funny thing. So if you're saying, oh, there's this fine-tuning problem of 120 orders of magnitude difference, you could just write it in different units, and all of a sudden it's way less dramatic. And so, but at the same time, it's still an interesting question. So there's a lot of things that we don't know. We know something's wrong, but we don't know what. And there's some assumptions that went into creating this problem in the first place. One of them is that the universe is homogeneous and isotropic. And it's clearly not on small scales, but on larger scales it is, and we can measure this. Gravity is well described by general relativity. That's not something that is, technically completely established, even though, of course, general relativity has passed with flying colors all kinds of tests. Maybe there's some kind of modified theory of general relativity that in certain circumstances you might have a various theory of Mond that better describes the equations of gravity. That could be the case. But then another thing is that the reason for this accelerated expansion is actually the vacuum energy. Maybe there's something we're missing. It's a rather natural idea that there was already room for it, and it already fit in the equations of general relativity, and it has all the required properties to cause an acceleration in the expansion of the universe, as we looked at with the Friedmann equations last time. But at the same time, these are things that that are possible solutions to the problem. Another solution is the so-called miracle solution. So it's that if you look at the top equation, it's that, well, what we actually measure is the effective cosmological constant term. And as a result, that's really small. But you see on the right-hand side, there are two terms, and the two on the right don't need to be small. They could be really large, but just such that when you add them together, it creates a rather small value. And so it's, of course, kind of funny that the term that you get from quantum field theory, it was rather interesting to me that because of the successes of QFT in the standard model, some even write in papers that the term you get from quantum field theory should be considered measured, even though we've never actually measured that term. It's just a calculation that we've done. But you can't actually measure that term directly. But because we're so confident in our theoretical models, it should be as good as measured. But that's a little silly, I think. But then there's this bare cosmological constant. And so basically, what is that? Well, we don't know. There's just some kind of additional physics that cancels out all but the tiniest fraction of the value calculated from quantum field theory. So that's why Stephen Hawking once wrote in Grand Design, the calculation was wrong, or else some other effect exists that miraculously cancels out all but an unimaginably tiny fraction of the number calculated. And so basically, the bare cosmological constant is an interesting term. And what you could do is you could just say, well, I guess the calculation's right, and a miraculous fine-tuning has occurred. Or perhaps the calculation's wrong, which is why many cosmologists might say, I don't really see why this is so much of a problem. And I don't know. I mean, it seems like the problem probably lies in how we're calculating the energy density you get from quantum mechanics. But an interesting question is, are there other ways to measure the cosmological constant? Because really one of the only ways to do that is on the large scale cosmological measurements. But maybe if we could measure this locally, where we understand the dynamics and have a little bit more control over, well, the local effects, maybe that could work. And so this is an interesting question where basically if you solve out the effect that the cosmological constant has on the force of gravity, it's fairly simple to do. And there's the term of Newton's equations of gravity in the weak field limit, or Einstein's equations in the weak field limit, which basically equals gmm over r squared. And then you have a second term. And this term basically would effectively act as a repulsive force, where because of the cosmological constant, it would create this like anti-gravity force, negative outward pressure type of thing, and it's proportional to the radius, which on small scales, this is a negligible effect, but it would become increasingly important the farther out you get. And so it's an interesting thing. You can actually measure planetary orbits with a lot of precision and ask, what kinds of deviations do you get from Newton's equations of gravity? And it turns out if you do this, you can constrain the cosmological constant based upon measurements. And what you find is this term here where you find that the vacuum energy is less than 10 to the negative 32nd giga electron volts to the fourth power. I'm missing the fourth power there. That's pretty cool, but at the same time, that's a lot worse than the constraints you get from looking at basically large-scale measurements from cosmology. And so it does tell us something important, of course. It provides evidence for the cosmological constant, because whenever we measure this locally, we find that the value of the cosmological constant is less than this amount. So it also provides evidence that something is wrong with our quantum calculations. So that's a nice result. We can learn from that. But of course, an interesting question, another question is, wait, do these vacuum fluctuations really exist? That's a good question, because if we don't have any experimental evidence for such vacuum fluctuations, then why are we doing this calculation in the first place, and why is it even a problem? It's an interesting question. Typically, there are two pieces of evidence that are provided for evidence that this vacuum fluctuation is a real thing. One of them is the Lamb shift, and the other is the Casimir effect. And so the Lamb shift is a tiny difference between two energy levels that could be explained via a vacuum fluctuation. And so I won't go into too much detail. I'd encourage you to look that up if you're curious about it. The Casimir effect is interesting, where this is an effect that occurs when you bring two parallel plates close together. And as you do this, it's really interesting. This is the types of allowed wavelengths get less and less, such that basically you end up with some kind of outward pressure, or well, basically there's pressure on the outside and a lack of density of photons on the inside, and you end up creating this little vacuum-like thing in the middle, the closer and closer you press plates together. So it's really interesting. The only catch with this experiment is really fascinating, is that there are no actual photons in this experiment. This is an experiment that's effectively done in a vacuum. And so where on earth are these photons coming from? Where are these waves coming from? Well, they could potentially be coming from the vacuum energy itself. Quantum mechanics allows for the creation of virtual photons, and this goes into a lot of different calculations and experiments that we have. And so this is a really interesting thing. Where do these virtual photons come from? Well, they come from the vacuum energy. So this is why this is provided as evidence that there is really some kind of inherent vacuum energy that exists because of this effect and the Lamb shift. However, is that the best way to describe these small effects? Well, there's a few links to here that I'll give you the PDFs, and it's a good question to ask. Because the high energy physics community says, well, yeah, of course, it's best to think of the vacuum energy as the reason why we see the Casimir effect. But then the condensed matter community says, no, 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 no. The Casimir effect has the same origins as the van der Waals force, which is a much, much more familiar force to us. And so as a result, it doesn't really make sense then to go ahead and propose some kind of hypothetical, really poorly understood explanation for the Casimir effect, but instead the van der Waals force, which is something that is part of just even the first semester that you would get in a general chemistry class. So that's an interesting question, because if that's the case, and this is better thought of in the sense of the van der Waals force, then the Casimir effect is no longer evidence that such vacuum fluctuations really do exist. Our best guess is that they do, but we're not quite sure yet. But then another question is that if these vacuum fluctuations really exist, do they gravitate? And what that means is that, sure, maybe these fluctuations are there, but they don't interact with gravity for some kind of reason. And if they don't interact with gravity, then they wouldn't contribute to the cosmological constant. And then again, there would be no problem. So it's fine if you get a really big value for the energy density of space from quantum mechanics if it doesn't interact in a gravitational way. So that's a really interesting thing. And of course, to really answer that question, we probably need an adequate theory of quantum gravity, which we don't have. And so perhaps in the future, that would be a solution to this, to understand how quantum mechanics and general relativity can come together. But we don't know yet. It's an interesting question. And so really, this isn't even a prediction in a sense. It's not that we were predicting to measure. This is really important. We weren't trying we didn't predict what the energy density should be and then go out and measure it and find that our prediction was really bad. So here's an example of a graduate level textbook that is just completely wrong. It said, this one in particular said, the simplest calculation involves summing the quantum mechanical zero-point energies of all the fields known in nature. This gives an answer about 120 orders of magnitude higher than the upper limits set by cosmological observations. This is probably the worst theoretical prediction in the history of physics. Nobody knows how to make sense of this result. Some physics mechanism must exist that makes the cosmological constant very small. But this isn't a prediction. The standard model doesn't predict the cosmological constant. Sure, you can calculate some kind of contribution due to various fields, but you can't measure that contribution. So those two effects, the Lamb shift and the Casimir effect, even if they are best thought of as fluctuations in quantum fields, we can't actually measure the overall strength of them. So we don't have a present way to measure any predictions or calculations from the standard model in the first place. And that calculation has a lot of uncertainties. If there are more particles, they would certainly play a role, but we don't know if there are more particles. Something is missing from our understanding of the standard model, but we don't know what it is yet. And so any calculation might be wrong anyways, because typically we might think, well, the standard model might be tweaked or amended at high energies. If there's some kind of supersymmetry, for example, that might look a little bit different. And again, this orders of magnitude thing really becomes smaller if you write it in different units. If you think about it in terms of particle mass, it's really only 14 orders of magnitude larger. And finally, as one cosmologist had pointed out, nobody quantifies goodness by taking ratios. You talk about uncertainty. You measure values. You plot error bars. And if you do that, if you write down the uncertainties of the standard model calculation, they're compatible with the measured value. So basically, this theoretical value or calculation that you get from the standard model is consistent with the measured value in the first place. And so that's really silly. There's something amiss here, but how it's typically phrased, certainly we have to be very careful about that. The last thing I have here are some interesting simulations about dark energy. And in particular, looking at variations of different values of the cosmological constant. Could it be different? It's an interesting question. So if you have no dark energy, it turns out that the star formation rate wouldn't have been much different. Basically, dark energy, if it was equal to 0, would have had very little impact on our universe until relatively recently. But all of the main formations of stars and of nucleosynthesis really wouldn't have been impacted. Here's an example of changing the value of the cosmological constant, going from 0 up to about 300 times its present measured value. And you find this is plotting the star formation rate against time. And so if the cosmological constant was, let's say, 300 times bigger, you'd still get a fair amount of stars. But star formation, compared to today, effectively would have stopped after about 5 billion years. And of course, the reason for that is that gravity would have been simply overcome by the density of the cosmological constant much earlier on in the universe. But you could have many variations on this. You could have maybe even up to 100 or at least 30 times, and you would still get a fairly compatible universe compared to the one that we see today. And so that's a pretty interesting thing. Here, another neat thing is that not only can we model the star formation rate over history, but we can measure the star formation rate over the history of our universe. And find that indeed our universe looked quite different in the past. And so this is really cool that we can do models and calculations on dark energy and the impact that it would have on star formation rates, but then we can compare that to actual measured values in terms of looking at the history of our universe. There's a graph on the left that talks about the star formation rate per year per megaparsec versus the redshift, and the graph on the right is an example of looking at different galaxies similar to the Milky Way galaxy going back in time. And you see that galaxies were quite a bit different earlier on in the universe. And so these types of measurements also help constrain and teach us something about dark energy. In particular, they tell us and you know how much dark energy there has, similar to these types of measurements as well. You recall here we looked at a number of these, looking at dark energy all in all, where you can have the fractional energy density of dark energy and the fraction of matter, and basically looking at supernova, cosmic microwave background, the amount of matter, the flatness of the universe, baryonic acoustic oscillations, you end up with a really, really narrow region that is consistent with all of the measurements that we've taken. And that region is in the region of an accelerating universe. So that seems to be where our universe is headed. And again, just a summary of dark energy is it's transparent. Its density is about 5 protons per cubic meter. And it's not even an energy as well. It's an energy density that doesn't dilute with inverse volume. If it remains constant, it's called the cosmological constant. But if it doesn't, it's a more exotic type of field. And the main evidence is, of course, the type 1a supernova, standard candles, the flatness of the universe, you have baryonic acoustic oscillations, the age of stuff in the universe, the deceleration and subsequent acceleration of the universe that you get from measurements and from the Friedmann equations, and ultimately the large-scale structure of the universe. And to come is the era of inflation. Really interesting question, and yeah, stay tuned for that.